two events are independent if the occurrence of one event does not in any way affect the probability of whether the second event is going to occur. And two events are dependent if that's not true, and the events do affect each other in a probabilistic sense. So on your homework, which I'm going to pass around soon, on your homework, exercise 1 asks you to come up with some examples of independent events and dependent events. I'll give you some examples. Like, what if you decide to sit down and you roll a die and you flip a coin? Event 1 is that you get heads on the coin. Event number 2 is you get a 3 on the die. Those are independent because it doesn't matter. The coin is not going to affect the die in any way. They're separate. On the other hand, a dependent example might be like, what if I reach into a bag of M&Ms, I eat one, and then I reach in again, and I eat a second one. And if I don't look in the bag, the color of the M&M that I get is random. But if the events are, well, the first one you eat is red and the second one you eat is red, those are dependent on one another. Because if I get a red M&M the first time, that decreases the probability that I'm going to get a red M&M the second time, because there's fewer red M&Ms in the bag to choose from. And if I don't get a red M&M the first time, then the probability is the same. So whether or not event number 1 occurs does affect the probability that event number 2 will occur for these dependent examples. So right over here, this example says, if you're watching sports, the Royals do not care whether or not the Chiefs win their next game. It doesn't affect the probability that the Royals are going to win, right? They're separate players playing on separate teams. They have nothing to do with each other. So those are independent events. Over here, if I say the first card you deal is a diamond, and the second card you deal is red, those are dependent events because diamond is a red suit. And so if you've dealt one of the diamonds, then it decreases the number of red cards available in the deck that you could deal next. Again, the last example, independent events. Do you have a college degree or not? Did you eat chicken for lunch? Right? No bearing. I don't think that people with a college degree have any stronger preference towards or against chicken than people without. So those would be independent events. But on the other hand, if you're doing a demographic survey and you randomly select somebody and you say, okay, do you have a college degree and do you have an annual salary greater than $50,000 per year? That would be dependent because those are correlated. People who have a college degree, like a bachelor's degree, tend to earn more money, and so the probability of event 2 depends on the outcome of event 1. So independent and dependent. If you've got 2 independent events, then the probability of both events occurring is what you get when you multiply. You've probably seen this before, but this is the idea. This is something you should know. This only works for independent events 1 and 2. Here's an example. You decide to roll a die and flip a coin. What's the probability of getting heads on the coin and a 3 on the die? Well, the probability of event 1 occurring and event 2 occurring is going to be the probability of event 1 occurring times the probability of event 2 occurring. So what's the probability of flipping a coin and getting heads? 1/2. That's a theoretical probability. I could either get heads or tails, 2 choices, 2 possible outcomes, one way that I can get event 1. The probability of event number 2, again, there's one side of the dice that's labeled as a 3. There's 6 sides of the dice, so there's 6 total possible outcomes. And then 1/2 times 1/6, you multiply across the top, 1 times 1 is 1, multiply across the bottom, 2 times 6 is 12. So the probability is 1/12, right? the simplest example that you can remember, keep in the back of your brain about independent events and probabilities. If I have a third event, such as, what if I draw names out of a hat, and there's 32 of you students here. So what if event number 3 is that I draw my own name out of a hat with 33 of us present, so that would be 1 out of 33 for the probability of event number 3. Well then, what's the probability of event 1, event 2, and event 3 all occurring? That's going to be 1/2 times 1/6 times 1 over 33. So if you have multiple events, more than 2, even more than 3 events, and they're all independent of each other, the probability that all of the events will occur is just multiplying, okay? All right. Here's another example. What if you watch sports on the TV? If the Chiefs have a 60% chance of winning their next game, and the Royals have a 55% chance of winning their next game, what's the probability that both teams will win their next games? So we're talking about probability of event 1 and event 2. This is the thing. This is the rule we memorize for 2 independent events. And so the Chiefs, we're talking about 60%. The Royals, we're talking about 55%. Now we remember that percent means divide by 100. And so we're talking about 0.6 times 0.55. And you could use your calculator on a test to figure out what is 0.6 times 0.55. I'm going to use my calculator right here, so we have a nice answer here to this example, and it's 0.33. As a percent, that would be 33%. So there's a 33% chance that both teams are going to win their next games. All right, I'm just going to give you 2 examples because I don't want to beat this into the ground. But does anybody have any questions about what we're doing here? Okay. Next, a slightly trickier example. Compute the probability that at least one male out of 1,000 aged 24 years will die during the course of the year if the probability that any 24-year-old male survives the year is 99.86%. This is kind of a morbid example, but I got this from a textbook. So basically, choose somebody 24 years old male. Probably nobody in this class is 24 years old, but maybe you can relate to this slightly. I know that my chances of making it to September 26th, 2026 is probably like 99.86%. It's almost guaranteed, but it's not quite guaranteed, right? So there's a small chance of dying during the course of the year. And what we're saying is that we're taking a large cohort, like 1,000 people to follow, and we're going to follow this group of 1,000 people for 1 year and see what happens. There's a chance that maybe nobody dies, right? Maybe all 1,000 people are still alive and breathing at this time next year. But the question is asking, what's the probability that at least one of them is going to die? So let's start writing down some things because it can help us think through the problem. We want the probability that at least one dies. It could be 1, or it could be 2, or it could be 3, or it could be more. But we want the probability of at least 1. This is the complement of nobody dying. Does that make sense? Do you remember what complement means? Complement was a vocabulary word from 3 days ago. We said the complement of an event is the set of all possible outcomes that are not included in the original event. And so if my original event that I care about is at least one person dying, the complement of that is that nobody dies. Right? And the complement rule from last time said I can calculate probabilities using the 1 minus thing, because the probability that no one dies plus the probability that at least one person dies has to be equal to 1. We rearranged that equation and we got this. This is the complement rule. Okay? So the probability that nobody dies is going to be equal to the probability that our guy number 1 lives times the probability that guy number 2 lives times the probability that guy number 3 lives times the probability that guy number 4 lives throughout the year, and so on. And I don't have the patience to write out all of these, but there's supposed to be 1,000 people, right? There's 1,000 guys that we're tracking. And the probability that any one of these people lives is 99.86%. And they're all independent of each other, right? Maybe not exactly if some of them know each other and they carpool to work, right? Because then it's a little bit dependent if they get in a car wreck. But for the sake of this question, let's assume that the probability of each one surviving the whole year is going to be independent of the others. And so I can use this rule. I can just multiply all of these together. And that means the probability that no one is going to die is going to be 99.86% times 99.86% times 99.86%, and on and on and on, 1,000 times. Well, that would be the same thing as 0.9986 raised to the power what? 1,000. Because whenever I do an exponent like that, that's just repeated multiplication. And I'm saying, let's repeatedly multiply 0.9986 1,000 times. So this is where you can pull out your calculator, and we can say 0.9986 raised to the power 1,000. And I got the number 0.246. Is that my answer? Nope. That's not my answer. What I actually want to know is the probability that at least one person dies, and that is 1 minus 0.246. So 1 minus 0.246 is going to be 0.754, which is 75.4%. So it's a little bit of a sad fact, but you know, at least individually, people have a 99.86% chance of surviving till the next year. But if you really care about following a group of 1,000 people, what's the probability that at least one of them is going to die? Well, it's actually like a 75% chance that you're going to be mourning at least one person. So it's a bummer. All right, any questions about how we did this? Does the whole chain of reasoning work for you? Okay. Conditional probability. Let's talk about conditional probability. The conditional probability of event number 1 given event number 2 is the probability that event number 1 is going to occur in the hypothetical scenario where we already know that event 2 has occurred or will occur with certainty. So the way we write this is I write capital P for probability of event number 1 given event number 2. So this vertical line here, when you read this out loud, you say the word given. This is the probability of event number 1 given event number 2. And an example says, what is the probability that a randomly selected male is divorced? So this is a question asking about a conditional probability. It's saying, what's the probability of divorced given we know they're male? Does that make sense? The probability of selecting a divorced person is different now that we specify that they're male than it would be if we just randomly selected a divorced person out of the whole population. So this is a conditional probability on the condition that they are male. And so this probability of divorced knowing that they are male, man, I should really add the total to this table because I hate having to add 46 plus 63.3 plus 3.3 plus 12.1 plus 2.2, 126.9. 12.1 divided by 126.9 is 0.0954, and that's the same thing as 9.54%, right? But again, if I were going to do this for the entire population, or if I was going to do this for just the females, I would get a different probability. So the probability of divorced given that they're male is an important part of the equation here. What is the probability that a randomly selected divorcee is male? So this time we're asking, what's the probability that we randomly select a male given that we are only selecting from the divorced group? And this is different, because this is going to be 12.1 divided by 28.2. There's going to be 0.429, which is 42.9%. So it matters the order in which you put things inside the parentheses, right? The probability of male given divorced is different from the probability of divorce given male. Yeah?
So when I take divorce, I take males and females. That's why we divide by 28.2.
Yeah. The question is asking, what's the probability that a randomly selected divorcee is male? So when I say a randomly selected divorcee, what I'm saying is only think about this group of people, because this is the group of people that have been divorced. And the total number of divorced is 28.2. And then if I'm selecting for males among the divorced, then that's what goes in the numerator. Good question. Other questions? Does this make sense still? Okay. So this is called the multiplication rule for dependent events. Multiplication rule for dependent events. And if I've got two dependent events, meaning their probabilities really do impact each other, the probability of both events occurring is this. They are the same, by the way. I know these formulas look different, but these mean the same thing because numbering one event 1 or 2 is arbitrary. The word arbitrary, that just means it doesn't matter, right? I could say that, hey, this event is event 1 and this event is event 2, or just arbitrarily, I could say this is event 1 and this is event 2. And it doesn't matter how I order things. So I should be able to switch off the 1s and the 2s as long as I switch every instance when I see the 1 and the 2 and get the same numbers. But you'll notice the difference between multiplying for independent events and multiplying for dependent events is that I have to include the conditional probability of event 2 given event 1, not just the overall probability of event number 2. So let's look at exercise number 5. Without looking, you reach into a bag of M&Ms and eat one, then repeat. What is the probability that the first 2 M&Ms you eat are both red? And let's look at this photo. I think there are 3 red M&Ms. And how many total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 19 total. So what's the probability? And I should be really clear about this too. Let me write event 1 is that the first M&M is red. Event number 2 is that the second M&M is red. What's the probability of event number 1 happening?
Three out of 19.
3 out of 19. What is the probability of event 2 given event number 1? Two out of what?
19. Or 2
You're
out
close.
of 18.
Yeah, 2 out of 18. Very good. So when I pick out the first M&M, there's 3 different ways I could choose a red one. There's 19 total possible outcomes. When I pick out the second one, it depends on the color of the first M&M. If I picked out a red M&M first, now there's 2 possible ways of getting another red M&M, and there's 18 total possibilities. But if I had picked a green M&M first, then this would have been 3 out of 18, because this probability depends on whether or not the first event had the outcome. And so what the question is asking us for in the end is saying, what's the probability of getting 2 red M&Ms? That's event 1 and event 2. And since these are dependent, I'm going to use this formula and say that must be equal to the probability of event 1 times the probability of event 2 given event 1. And that's going to be 3 out of 19 times 2 out of 18. And 3 out of 19 times 2 out of 18 is 1.75%. It's a lot smaller than I thought it would be. Does that seem right? Okay, questions about this? So hopefully you can identify when 2 events are dependent on one another. You understand what the notation means for the conditional probability notation. We'll do one more and then we'll move on. You draw from a deck of cards without replacement. So you're not going to put the card back, you're going to keep it. If I say without replacement, I mean keep the card, don't put it back. What is the probability that the first card you draw is a diamond and the second card you draw is red? So here are the diamonds. And here are the red cards. And let's call the first card diamond, event 1. And then second card red will be event 2. So we're talking about the probability of event 1 and event 2 occurring. And that's going to be the probability of event 1 times the probability of event 2 given event 1. Okay, what is the probability of drawing a diamond on my first card? 1/4. Because there's 4 different suits. 1, 2, 3, 4. And I'm okay with drawing any diamond, so the probability is 1 out of 4. What's the probability of event 2 given event 1? Mm-hmm. 25 out of 51. Because if I start off with 26 red cards, and I've already picked one out, and there's only 25 cards remaining. Start off with 52 total cards, but I already picked one out, so there's 51 total cards remaining. And so this is going to be 25 over 204, also known as 12.3%. And for your answers on this next test, I don't care if you want to leave it as a fraction, full credit if you leave it as a fraction. I don't care if you put it in your calculator. I'll give you full credit if you put it in your calculator. But just give me one of the two. And that is fine either way. Okay, did this make sense to everybody? Questions? Okay. A few more examples. I think maybe 2 more examples I want to show you. Class has gone by really fast today. This is called Bayes' rule. And we get Bayes' rule. I want to show you where it comes from. I want to develop a little bit of mathematics understanding here. So let me just show you where we might invent Bayes' rule. We say, where did my rules go? Right here, okay. Right here. So we talked about how these are the same. It's the same formula, and it doesn't really matter which event I label event 1 or event 2, right? So I could use either one, the first row or the second row, to calculate the probability of both events happening. Event number 1 and event number 2 would be the same thing as event number 2 and event number 1. They both have to happen. And so what if I take this right-hand side, the probability of event number 1 times the probability of event number 2 given event number 1. And we set it equal to, what's a good color? I'll do this color. I don't use this one very often. This right-hand side, which is the probability of event 2 times the probability of event 1 given event 2. Okay? They should be equal to each other. They're both equal to the probability of both events happening. So these are equal to each other. This is a completely valid equation that I just wrote down. Okay? If you divide by the right factor, this is what you should get, right? Go back to that equation, divide by the probability of E2, and what you'll get is instead on one side of the equation, the probability of event 1 given event 2, and then on the right side of the equation, everything else. So this is important to know, or it's important to put on your little 8.5 by 11 page of notes for the next test. And I might ask you a question like this. Okay, at the state fair, 70% of people eat a deep fried Oreo. 55% of people eat a funnel cake. And among those people that ate funnel cakes, 90% of those also ate a deep fried Oreo. We can just stick to the Bayes rule formula too, but we've got to label which is going to be my event 1 and which is going to be my event 2. Event 1 is going to be Oreo. Event number 2 is going to be funnel cake. Let's just follow this formula and see if we can get what we're after. We want to know what is the probability that someone ate an Oreo. No. What's the probability that they ate a funnel cake given the fact that we already know they ate an Oreo? And this doesn't exactly match my Bayes rule formula. So what I could do is I could just change the way I've lettered or numbered, change the way I've numbered the events. There's nothing that says event number 1 has to be Oreo and event number 2 has to be funnel cake. Maybe I should make event number 1 the funnel cake and event number 2 the Oreo. And now I can just copy down my Bayes rule formula exactly. And that's what I meant earlier whenever I told you the numbering of the events is completely arbitrary. I can change the numbering if I want to match what I already have written down as a formula. Okay, what's the probability of event 1? What's the probability that someone ate a funnel cake?
55%.
Perfect, yep. Out of the total population, 55% ate a funnel cake. What's the probability that someone ate an Oreo out of the total population? 70%. What's the probability that someone ate an Oreo given that you already know they ate a funnel cake?
90.
Yes, 90. There we go. So that's going to give me the right probability. I just got to multiply 0.55 times 0.9 divided by 0.7. And I get something pretty close to 0.7. It's going to be 0.71, 0.707, which is the same thing as 70.7%, just barely more than 70%. All right, if we randomly select an attendee who ate a deep fried Oreo, the probability that they also ate a funnel cake is 70%. Only 55% of the total attendees ate a funnel cake, but among the people who ate an Oreo, it went up to 70%. All right, last problem. Suppose 2% of the adult US population has undiagnosed cancer. Got a lot of morbid examples today for you. There exists a blood test to determine whether an adult has cancer. The test has a 95% probability of correctly reporting a positive result for people who have cancer. So if you have cancer and you get a cancer test, it should come back positive, right? 95% accuracy. And the test has a 95% probability of correctly reporting a negative result for people who do not have cancer. Because if you don't have cancer, you want to have a negative result. Suppose you're a doctor and you see a patient and their blood test comes back positive, remember, which indicates that your patient has cancer. What is the probability that the patient standing in front of you really does have cancer?
95%.
You'd think so, right? There was I don't know, this has maybe been like 5 or 10 years ago, but there was a statistician, a guy who with his PhD in statistics, went to give a talk at a convention where doctors were, right? Like people who have their MD, medical doctors who were practicing medicine. They had this convention, and the statistician gets up to talk, and he asks this exact question to the room full of doctors. And he has them respond using a little app on their phone. They give a poll. They said, what do you think the probability is the patient actually has cancer? And like the vast majority of doctors, like 99% of the doctors, right, all answered 95%. The test is 95% accurate both ways. 95% chance the patient has cancer. They would all be wrong, right? Even doctors don't know everything. I'll show you how to actually calculate this probability. To start with, imagine that today 1 million people across the United States are going in to get their blood test, right? So out of these 1 million people, how many of them actually have cancer? 2%, right? 2% of 1 million. And so 2% of a million looks like 20,000. So 20,000 people have undiagnosed cancer. The rest, which is 980,000, do not have cancer. I think that's right. Okay, well, what about these people who do have cancer? We can split them into 2 groups. For the people that have cancer, they have a 95% chance of getting a positive test result. And so if I multiply 20,000 times 0.95, that means that 19,000 people have cancer and got a positive result. That means the remaining 1,000 people have cancer and got a negative result from this initial test. Okay. What about these people that don't have cancer? Some of them got a positive result, right? There was only a 5% chance because they don't have cancer, but there was a 5% chance that even the people who don't have cancer got a negative result. So let me multiply 0.05 times 980,000 people. And I got 49,000 do not have cancer, but still got a positive result out of an error. Okay? Then, out of those people who do not have cancer, there was a 95% chance that they got a negative result, because that would be correct for someone who doesn't have cancer. And so that would be a group of 931,000 people that do not have cancer and got a negative result. So, what do you as the doctor actually know about the patient walking through the door? You don't know whether they really have cancer or not. The only thing you know is that they got a positive result. That means your patient belongs to one of two groups of people, okay? Your patient is either in this group that got a positive result or in this group that got a positive result. So the probability that your patient really does have cancer, given that they received a positive result from the test, is going to be 19,000 divided by 19,000 plus 49,000. In other words, 19 over 68. And 19 divided by 68 is 27.9%. So you've got a test that's 95% correct at diagnosing people with cancer when they really do have cancer. And the same test is 95% correct at telling people they don't have cancer when they really don't have cancer. But even in this situation, you're a doctor, a patient walks in your door, they test positive, they still only have a 28% chance that they actually have cancer. Okay? So what do you do as a doctor when someone gets a positive cancer blood test screening? They don't immediately start you on chemo drugs because that would be reckless and irresponsible. What they do instead is they say, we're going to send you for further testing. And that's when you get MRIs and stuff to actually see if they can test cancer with an even more accurate test. But this is a pretty, I think, surprising result for a lot of people. I think that a 95% accurate test really doesn't tell you that much. But the driving factor here, you can probably tell, is that only 2% of the population have cancer. So when somebody walks into your room, chances are they don't have cancer, right? Before you do the test, there was a low probability that they had cancer to begin with. That's what makes this number so skewed. But that's the correct answer.